In this video, we are going to talk about how we can use SALT to help us conduct a hypothesis test for two proportions. And I'm going to use that example from Khan Academy that you saw in the previous video, and we're going to walk through how to do that. Hypothesis testing works the same whether you're doing one proportion or a t-test for the mean, or a two proportion or a two mean. Or we can do it for standard deviation and variance and so on. It's all about figuring out what your hypotheses are going to look like, and then figuring out what your p-value is, comparing p-value to your alpha value. So let's look at this one. Researchers suspect that myopia or nearsightedness is becoming more common over time. A study from the year 2000 shows that 132 cases in 400 randomly selected people, and a separate study from 2015, which is 15 years later, shows 228 cases in 600 randomly selected people. So I'm going to pull up a piece of paper so I can write. And we're trying to show, or we're trying to analyze this statement. So we're testing the claim that it's becoming more common over time, which means that we would expect more in 2015 than we would in 2000. So that's giving us that alternative hypothesis. So H1, we would expect more in 2015 than we do in 2000. And then the null hypothesis would be that they are equal. Now, there's different ways to write this. We could write this comparing the two populations. Sometimes you'll see it written this way, where everything is moved to one side. So if I were to subtract this guy over using just a little bit of algebra there, I would get H naught of 2015 minus, sorry, P naught of P hat of 2015. I cannot talk today. P of 2015 minus P of 2000 would be equal to 0. And another way to write the alternative, if we were to move over this p-value, we would have P of 2015 minus P of 2000, and that would be greater than 0. So you could see it written either way. They do mean the same thing, though. So let's type in what we know. We're going to start with 2015, and the reason that one's first is we're trying to determine whether or not it's more common over time. So this year occurs later than that 2000. So our P1 is going to be 2015 information. So in 2015, we had 228 cases out of the 600 cases. And then in 2000, which is going to be our second variable, we're going to have 132 out of 400. And we are doing a hypothesis test. And we are looking at greater than 0. We're going to use this to help us figure out what to choose here. We're going to generate the results. So you can see that our z-test statistic, if we were to use the formulas, is 1.61. And that's the same thing that they got in the Khan Academy video using the formulas. And the formulas, as we get more advanced, are just not going to be as nice. And then the p-value. That's going to be 0.0533. So then our next step would be to compare P to alpha. Now, in this case, they did not give us an alpha value. We could say, what if they wanted alpha to be, what if alpha was 0.05? Then our p-value is greater than alpha, so we would fail to reject. Okay, but what if they wanted to control it a little bit more tightly and use 0.01? Then our p-value is still greater than alpha. But what if they wanted it to be a little more loose? What if alpha was 0.10? Then our p-value is less than alpha, and then we would reject. So it would really just depend on what they wanted for p. And then we could use our table from Triola, or from our book, to help us figure out how we would phrase that final conclusion. So let's look at one from the textbook. Random samples are selected from two populations. The sample from population 1 has a sample size of N1 equals 85. And the proportion of success is 0.44. Sample from population 2 has a size of 81, and the sample proportion of successes there is 0.95. Calculate the value of the test statistic that could be used to decide if there's a convincing evidence that the actual proportion of successes in P1 is less than the actual proportion of successes in P2. So there's our alternative hypothesis. We want to know, is the successes in proportion of successes in P1 less than the proportion of successes in P2? So the null would be P1 is equal to P2. And again, we could write that this way by moving everything to one side. Once again, we're going to have to figure out what our x value is. So let's do that. We know that x over n, I'll call that x1, has to be equal to 0.44. So our x1 value, if we were to multiply 0.44 times 85, I got 37.4. So let's round that to 37. We're going to do the same thing here. X over 81 is equal to 0.95 multiplied 0.95 times 81. And I got x2 to be 76.95. So let's go with 77, rounding. Now we've got all the information we need to substitute in. Number of successes is 37. The number of trials was 85. And our second sample, we had 77 out of 81. And this time we were looking at less than. And we are doing a hypothesis test. So notice that SALT's going to really want us to interpret this way so that we can use its software. Generate the results. And then our Z statistic is going to be negative 7.16. That is super small. So our p-value is approximately 0. So it's less than 0.00001. And in this case, p is definitely going to be less than alpha, which means we are going to reject H. So let's look at another example. The authors of the article titled Adolescents and MP3 Players, Too Many Risks, Too Few Precautions, was published in the Journal of Pediatrics, concluded that more boys than girls listen to music at high volumes. This conclusion was based on data from independently random samples of 764 Dutch boys and 748 Dutch girls aged 12 to 19. Of the boys, 397 reported that they almost always listened to music at a high volume setting. Of the girls, 331 reported listening to music at a high volume setting. Do the sample data support the author's conclusion that the proportion of Dutch boys who listen to music at high volumes is greater than the proportion for Dutch girls? And we're testing at the 0.05 significance level. So this is the claim that we're looking at. So I'm going to highlight that. So we're testing the claim that the proportion of Dutch boys, so now I'll use PB here, who listen to music at high volumes is greater than the proportion for girls. So the alternative, the null would be that they are equal. Now remember, we can write that as H naught PB minus PG, and then H1 PB minus PG. So this would be equal to 0 because I could move this over and I would have 0 here. If I move this over, this would be greater than 0. So we're looking at a right-tailed test. So let's collect all of our information. So we had a total of 764 boys and 748 girls. Of the boys, we had 397 that listened to loud music, basically, and girls, we had 331. So let's type everything into SALT. To sample proportion, looking at boys first, right? So there's a total of 764. Our X is 397. And then for our second variable, which would be girls, we have 748 out of 331. And we are looking at a right-tailed test that we are going to choose greater than. Generate some results. So if we look at our test statistic here, we've got a 3, and then the corresponding p-value is 0.001. We were testing this claim at, I think it was 5%. Yep, 5%. So our p-value is less than alpha. P is less than alpha, we reject. H naught. So how would we phrase that final conclusion? We're going to go back to our table. The original claim does not have an equality, and we rejected H naught. So there is sufficient evidence to support the claim that the proportion of Dutch boys who listen to music at a high volume is greater than the proportion for Dutch girls.